Hello students, let us continue our discussion on current electricity. And in the last session, we were discussing about Wheatstone's network. As I said, Wheatstone's network is a theoretical network, okay, which will help us in many practical application. The balanced condition of Wheatstone's network is the current through the galvanometer should be 0 and the result of that is P by Q is equal to R by S. Okay. So, balanced condition is, when do we say a Wheatstone's network is balanced? We say a Wheatstone's network is balanced when the current through the galvanometer of the Wheatstone's network is 0 and or because even when Ig is equal to 0 it is said to be balanced, or even when P by Q is equal to R by S, then also the Wheatstone's network is said to be balanced. Okay. If P by Q is equal to R by S is true, Ig will be 0, or in other words, if Ig is equal to 0, P by Q is equal to R by S will be true. Okay. So, that is about Wheatstone's network and its balanced condition. Now, moving ahead, today we shall see one of the practical application of Wheatstone's network. Okay. So, we will take the theory part of Wheatstone's network and we will apply it practically. Okay. So, how does a Wheatstone's network look like? You all know that it's a quadrilateral shaped network where you will have 4 resistors. These points are named as A, B, C and D, and these resistors are named as P, Q, R and S, and between the terminals A and C we will connect a cell or a battery, and between the terminals B and D we will connect a galvanometer, and that galvanometer will have its own resistance. This is the circuit diagram of Wheatstone's network, right? This is circuit. Now, if I take the same circuit and draw it in a different way, that won't make any difference as of the connections are considered, which means I am going to take the same circuit and just change the shape of the circuit from this shape to a new shape, but I will keep the components in their proper places. Okay. Just observe, I will simply take the point A here. Now, instead of this part, this is a conductor, and instead of simply putting a conductor, what I will do is I will put an L-shaped metal strip. Okay, L-shaped metal strip, which is very similar to a metal scale, but L-shaped one. Okay, this part. Okay, clear? And I will just leave a gap, and this part from P to Q, again you have a conductor. So, I'll put one more metal strip. Okay, instead of this conductor I will put metal strip. See, keeping a metal strip and simply a conductor will not make big difference in the circuit. They are one and the same. Basically they are conductors, and those conductors will have very less resistance. Even these metal strips also has very less resistance. Yes, we can also make use of simple wires, but if we make use of metal strips, the resistance will be very less, and we don't want resistance between the conductors or through the when the current flows through this conductors part. Okay, we don't want resistance to be there. So, we will make use of metal strips so that the resistance is very less. Why is the resistance very less for a strip when you compare it with the conductor? Conductor means a simple wire. Okay, I am talking about simple wire like this. When you have a simple wire, the area of cross section is very less, right? When you have a metal strip, okay, the area of cross section is larger. So, when you have area of cross section larger, you can get less resistance from that kind of conductor, right? So, in order to get as less as resistance possible, we will make use of this kind of metal strips instead of simply keeping them in the form of wire. Okay, right. So this part is done. This is again I have taken the test, another metal strip, and this is point B. Okay, clear on that? Next, from this point to this point, here you have C, and similar to this L-shaped strip, I'll put one more L-shaped strip here on the other part of the network, and see, this is point C. Okay, clear with them? Now you can just imagine where are the resistors P and Q should be connected. Now you see, resistors P and Q should be connected here. P should be connected here and Q should be connected here, right? So here I will have the resistor P, and here I will have the resistor Q. Clear? The upper part of the circuit is done. Now coming to the lower part, here you have resistance R and S connected between AD and A and D and D and C. So instead of repeating the same way, I will just make use of a 1 meter wire, okay, 1 meter metallic wire that is fixed between the terminals A and C. Okay, this is 1 meter metallic wire, a conductor fixed between the terminals A and C. Now, where is the galvanometer? Okay, before we come to the galvanometer, resistor R, resistor S, let me connect the battery or the cell. So the cell should be connected between A and C, no? So this is where I will connect the cell. I will have the key now. Okay, this is just key, this is the circuit symbol of key. If I put a dot inside this key, then we say the circuit is closed and hence there will be current in the circuit. If I remove this dot, then we say the circuit is open and hence there is no current in the circuit. Okay, right. So this part is done, the upper part is done. Now I need to put the galvanometer. I will connect, see, the galvanometer is starting from the point D. Okay, so this is where the galvanometer will come. And instead of connecting it to point D, what I will do is I will connect this other end of the galvanometer to a sliding device which is called jacky, which can slide. Okay, it's a sliding device with a wire connected to it, and this sliding device can slide on the wire AC freely. Okay, clear on that? So this jacky or this device, the sliding device is called jacky. You will get to know when the lab starts. So this device can slide over this wire A and C. See, now I have chosen the wire AC which is of length 1 meter exactly, and this wire will have its own resistance, isn't it? Every conductor will have its own resistance. Similarly, even this wire will have its own resistance. So the entire wire has its own resistance. The point where I keep the jacky is named as point D. Okay, and the left part AD is said to have the resistance R. Okay, see here on the top part we took external resistance P and Q, but in the lower part of the Wheatstone's network applied practically, we will take the resistance of the wire itself as the resistance R. Clear on that? Here we have separate resistors P and Q, but in the lower part we will not connect any extra resistance. Instead, we will consider the resistance in the wire, because it's a metallic wire, it will have its own resistance. So the resistance in the wire itself is considered as resistance R, the points between the resistance between A and D. And similarly, look at this part D, between D and C, you have the other part of the wire left, and this other part of the wire left will have its own resistance, and I can call the resistance in this part of the wire left as resistance S. And now you can see the entire Wheatstone's network is completely converted into a practical form. Okay. Now, what is the advantage of this practical form, and in the first place, what is the name of this practical form of the Wheatstone's network? This practical form of Wheatstone's network is called meter bridge. Remember, this wire will have 1 meter scale connected just or fixed just beneath it. Okay. So, this 1 meter wire will have 1 meter scale fixed just beneath it. Okay. It will be fixed just beneath the metallic wire, because we need to know at what length are we stopping the slider. Okay. Right. So, what is a meter bridge basically? A meter bridge is the practical form of Wheatstone's network with 1 meter wire connected between the terminals A and C. Okay, 1 meter wire connected between the terminals A and C as shown in the figure, and P is the excuse me, P is the wire of unknown resistance. Okay, here instead of, I can keep a resistor, that is not a problem, but if we are designing a practical form, there should be an application of that practical form, isn't it? Without practical application, why do we need to design design an experiment? Yes. So, we have designed this experiment because we have an application, because we are going to make use of this device, this apparatus, to obtain the unknown resistance of a wire. Okay. You take any wire that you know, okay, any kind of wire that you know of any length, which is normally between, say, somewhat like few centimeters to 1 meter, 1.5 meter, 2 meters you can take. Now, your intention would be to get the resistance of that wire. How to get that? Yeah, you have simple formula and simple ways of V is equal to IR and all, but again there you are going to get stuck with the EMF and TPD forms, and it is going to become complicated when you simply connect a cell and get the current through that, because there are many complications involved. Because you see now the intention is to get the resistance of a wire. Okay. So, one experiment that we might have done to get the resistance is take the wire, okay, connect it to a battery, a cell, a small cell, and then put a ammeter. Okay, there is a device which is called ammeter, which can measure current, and you also put the voltmeter across it. So, this setup will also give you the resistance of the wire, but the problem is when the current flows through the wire, this ammeter will have its own resistance. So, that will affect the final value. Similarly, this voltmeter connected will also draw some current to it, following, because it has to work, it has to show the reading, what is the voltage across the terminals. So, in order to do so, this voltmeter has to draw the current through that, and hence you are not getting actual current. One more thing, this ammeter will have its own resistance, which is added with the resistance of the wire. So, a simple apparatus setup like this will not give us the exact resistance of the wire. Okay. Yeah, it will give approximate value, but in order to get the better value of resistance of a wire, we shall make use of this meter bridge. Okay. So, meter bridge is a device with 1 meter wire stretched and connected between the terminals or the points A and C, and an L-shaped metal strip is connected to point A, and another L-shaped metal strip is connected to point C, and one more straight metal strip is inserted between the L-shaped metal strips with certain gap, and these gaps are connected. Okay, these gaps are connected using using a wire. This is a resistance which I have represented, but this can also be replaced by simply a wire of unknown resistance and a standard resistance connected here. Okay, in this part of Q, we need to connect a standard resistance. Standard means we have standard resistance already with us, like 5 ohm, 10 ohm, 20 ohm and all. We can get the standard resistances, and we should put that or connect that standard resistance Q between these 2 points as shown in the figure. Okay, so keep one thing in mind. Here P is a wire of unknown resistance, not the standard resistor. Q is the standard resistor. AC is a wire of length 1 meter, and we will connect a cell between the terminals A and C as shown in the figure. From the point B, the connection is given to galvanometer, and the other point of the galvanometer is given to a slider which can slide on the wire AC. Okay, so this pointer can slide across on the line on the wire AC. Now we can stop the sliding when the galvanometer shows 0 deflection. Okay, when does the galvanometer show 0 deflection? When the current through the galvanometer becomes 0, then the galvanometer shows 0 deflection. Okay, so at certain point D, because we can get various points while sliding, but at one particular point the deflection becomes 0. Okay, let D be the point when the current through the galvanometer becomes 0 and galvanometer shows no deflection, okay, or 0 deflection. Okay, so D is the point when the galvanometer shows no deflection, means no current. When the galvanometer shows no deflection, what do we say? We say that the meter bridge or the network is said to be balanced, isn't it? That's what the basis of balanced Wheatstone's network. So when at point T, at point D on the wire, okay, see this slider can move right from here to here. I can move it, but I will stop the movement. I will stop sliding when the galvanometer shows no deflection. At point D on the wire, when the galvanometer shows no deflection, the network is balanced, right? That is what is the balanced condition of Wheatstone's network, and this is also a Wheatstone's network itself in practical way. Now, when it is exactly balanced, current is 0, and when the current is 0, what is the relation between the resistances? So I can say when the network is balanced, which means when the current is 0, the network is balanced. The other condition of balanced network is P by Q is equal to R by S. What is our intention? Our intention is to get the value of P. What is P? P is the resistance of the wire which is connected between these 2 points, and this resistance is not known to us. We have to calculate it, right? And the resistance of this wire has to be calculated now. which means from this expression P has to be found. Clear? Now, do we know the value of Q? Yes, I have told you that this Q is the standard resistance which we will connect, which means we will be knowing the value of resistance that we are going to insert here or connect here. So, key Q value is known to us, but do we know this R and S? No, we do not know. We do not know the values of R and S. What are R and S? R is the resistance of the wire between the points A and D. What is S? S is the resistance of the same wire between the points D and C. Now, we do not know the values of resistances, but we do know the value of length from A to D, right? That is why we connect a meter scale here, and hence the name meter bridge. Okay. Here we will be having 1 meter scale just beneath that. So let me call the length of the wire from A to D. Okay, length of the wire, not the resistance. Length of the wire from A to D be L. And let me call the length of the wire from D to C. Okay, from D to C be 1 minus L. Okay, from here to here it is 1 minus L meters, because the total length is 1 meter, isn't it? The wire that we have considered is 1 meter wire. So, from here to here it is L, and hence from here to here it is 1 minus L. Now, what is the expression for resistance of a wire expressed in terms of length of the wire, area of cross section of the wire, and resistivity of the wire? The expression is R is equal to rho L by A, isn't it? You should remember this. Very important formula. Now, look at this. When we take the part, the AD part of the wire and the DC part of the wire, it is the same wire which is divided into two different lengths, isn't it? The wire is the same wire, 1 meter same wire, but it is divided in length. Okay, this length is different, this length is different, isn't it? So, length is varying for both the parts, part AD and part DC. What about the other factors? Is the area of cross section varying? No, we have chosen the wire in such a way that it has uniform cross section right from this point A to C. So, the same thickness. So, when you have same thickness, area of cross section of the wire does not change. So, for this particular case, resistance is independent of area of cross section. Okay, for this particular case, because see, now I want to compare this R and S, and what are the factors which are changing for this part of the wire and this part of the wire? Area of cross section is not changing, same area of cross section, and resistivity is also not changing, isn't it? Because it is the same wire. If I have taken copper, same copper from here to here, it's the same wire. If I have taken aluminum, same aluminum wire from here to here, aluminum, same. It's because it's the same wire. That's the basic thing. So, since the resistivity and the area of cross section will not change for this wire between the parts AD and DC, I can say resistance is proportional to L for this particular two comparisons, because I want to compare R and S. Now, if R proportional to L, what is S proportional to? Look at this. R proportional to L, S proportional to 1 minus L, right? More the 1 minus L value, more the S is. So, S proportional to 1 minus L, and hence in the place of R by S, I can write L by 1 minus L. Okay. This is all written, considered when the network is balanced in the first place. Okay. It should be balanced first, then all these conditions can be considered. When it is balanced, when the galvanometer shows no deflection, then it is balanced. Okay. Now, can we get the value of L from the meter bridge? yes, we can get it. That's not a problem because it's the length, simple length on the meter bridge, right? So we can get it. Can we get the value of 1 minus L? Yeah, it is very simple. Once we have L, 1 minus L is not a big deal. We can easily get it. And this L is kept in meters. So it is, if L is 0.2 meter, 1 minus L is 0.8 meter. That's it. Okay. Our intention is to get the value of P. We knew the value of Q and we now know the value of Q. That's not a problem. So P becomes equal to L by 1 minus L into Q. Okay. So this is the final expression where using which we can get the value of P, which is the resistance of the wire connected between these two terminals. And this is what we were trying to find. And P is equal to L by 1 minus L into Q. What is L here? L is the length AD, where D is the point when the circuit is balanced. How do we get the point D? D can be anywhere. D is the point where the circuit is balanced, or D is the point where the current through the galvanometer becomes 0. Okay. So we can get D using galvanometer. When galvanometer shows 0 deflection, we will stop sliding and hence we get D. Once we have the value of D at the point D, we can easily get AD. AD itself is L. So L we can get, 1 minus L also we can get. Q is standard that we will fix 5 ohm, 10 ohm, 20 ohm, whatever we want we can fix there. And we can get the resistance of a wire using meter bridge, using this apparatus meter bridge. Okay, clear with this? Very easy. We will actually do the same experiment in our lab. Then you will get to know the practical things of it. But now this is the entire theoretical part of meter bridge. Thank you. So dear students, this is the actual apparatus of meter bridge. Okay, see, this is what I have told. This is point A. Okay, and this is the L-shaped metal strip, and this is point B. Okay, and this is a straight metal strip, and here you again have a metal strip, and this is point C. Okay. Now, why the metal strips are chosen instead of simply conductors? Because these metal strips offer very less resistance. Almost zero resistance is offered because area of cross section is larger. Okay, so this is point A of the network, and this is point B of the network, and this is point C of the network. Now, here is the point between which we will conduct a wire of unknown resistance. Some wire of unknown resistance of some length is connected here, and here we will connect a standard resistance. How does a standard resistance look like? This is what is a standard resistance. Here, this is the resistance box, standard resistance box. Look at this resistance box, it is mentioned. If I remove this plug, this box offers 1 ohm resistance. Okay, and if I remove this, 2 plus 1, 3. Okay, if I close this, simply 2. So by using these keys, I can put, or I can get whatever the resistance that I want till 50 ohm. Okay, this is the standard resistance box. The other standard resistances are these. See, this is 2 ohm resistance. These are the terminals. Very easy. And here you have 1 ohm. Similarly, other standard resistances can be considered and connected between these two terminals, because we should know the value of resistance connected here, which is the value of Q, right? And we need to get the value of P here. Now, this is the sliding device that I was talking about, and this is the galvanometer. Okay, what I'll do, I'll connect a wire from point B to one of the terminal of the galvanometer, and this is positive, this is negative. Okay, from B to one terminal of the galvanometer. From the other terminal, I'll take a wire and connect to the slider. And now what I'll do is I'll start sliding on the wire like this. Okay. So while sliding, what happens is, as and when I connect, the galvanometer will show some deflection, and at some point while sliding, the galvanometer will show zero deflection, and that is when I can say the entire meter bridge circuit or the Wheatstone network is balanced. Okay. And hence say this is the point where the circuit is balanced, and see now the value of L from this point A and this point D will be 30 centimeter or 0.3 meter, and this part left here is 1 minus L, which will be 0.7 meter. Okay. And we will connect a battery between the points A and C. Okay. Between A and C we will connect a battery. Okay. This is the practical form of meter bridge. Yeah, I'll show you the exact working and the practical sessions. Thank you.